Okay, so this video is hopefully going to give a little bit more clarification on how to turn this example project into a piecewise function. So again, for your project, you and your group members are going to come up with a scenario that can be represented in a piecewise function. So we have possibly some different linear pieces. Maybe if we want to take it a step further, we can incorporate absolute value or quadratic, but for right now, we're thinking about a few linear pieces. The project asks that you have at least 4, and that you have readers, someone who's looking at your project, answer 3 questions. So we have the scenario here. Martin goes to school, and then we have 3 questions. The first question is going to be to write the piecewise function, and that was our focus in class today, and I'll kind of unpack that again here shortly. The second follow-up question that would be appropriate for this project would be to state the domain and range, and including the context of the problem as one of your project requirements. Third possible question would be question C. This kind of a follow-up question is asking, well, if Martin wanted to ride his bike, how soon is what time is he going to have to leave if he wants to get to school at 9 a.m.? So that is what your project would look like. But in addition to that, you're going to be responsible for providing an answer key. And that's what we're going to focus on in this video. So we're going to break down this piecewise function. We have a couple of different things happening as Martin commutes to school. So first and foremost, we notice he leaves his home for school at 7 a.m. and drives 10 miles in 15 minutes. He then stops for 30 minutes at that donut shop, panicking because he maybe spent too much time at the donut shop. He continues driving a little faster for another 20 minutes and covers 18 miles. Unfortunately, his car then breaks down and he has to jog the remaining 3 miles to school, and that takes him 45 minutes. So question 1 asks us to write the piecewise function for d of t. We've defined our variables, d to be distance in miles from Martin's home, so that will be important to include in your project. And then we've also defined time to be the number of hours since 7 a.m. And this was a pretty tricky component of this. Okay, there's a lot that went into converting this into a usable piecewise function. But we'll go through this bit by bit. So the first piece from 7 a.m. to 7:15, right? That first piece says that he leaves at 7 a.m. and for 15 minutes he drives 10 miles. Okay, so we have 10 miles in 15 minutes. We can convert that into miles per hour, right? Remember, we want our units, we have our miles for distance and hours for time. So we want to kick this into miles per hour. So we know that there are 60 minutes per 1 hour. And if you notice, the units of minutes cancel and we're left with what we are after as far as units go, miles per hour. Right? Some quick division or multiplication will show us that the rate that he's traveling here is 40 miles per hour. Okay, so we have a slope, right? The slope is 40 miles per hour, and we have a starting point for this segment of 0, 0. Okay, so this piece I'm going to say starts at 0, 0. No time has passed since 7 a.m. if he hasn't left his house yet, and no distance he hasn't accrued any distance from home if he hasn't left yet. So we can go ahead and put this into point slope form, right? Our 40 miles being our slope, our x minus 0 plus 0, and we see that that just simplifies to 40x. And I'm actually going to change that x to t, right? We have a t value, not an x value. So our first function is 40t. But we need to figure out what time values is this happening for. Given that we've defined time to be hours or fractions of an hour since 7 a.m. We want to come up with values, t values, that we could plug into our function that would allow us to figure out how far away Martin is from home. So looking back at this 7 a.m. to 7:15 time window that he's traveling at this rate, we can say that this started at a time value of 0 and ended at a quarter of an hour later. Okay, so he's traveling at this rate for the time value 0, or t is less than 0, less than or equal to 1/4. So we have a domain that corresponds with this first piece. This tells us that for the first 15 minutes of his commute, he's traveling at a rate of 40 miles per hour from a starting point 0, 0. Next, he stops at that donut shop. Okay, so at the donut shop, right, for 30 minutes, so from 7:15 to 7:45, he's actually staying 10 miles from home. Okay, so if you were to think about this graphically so far, I think just the graph, it's not required in this, but it's just something that will help us give a visual of what's happening. His distance from home changed in the first quarter of a mile, or sorry, not quarter of a mile, quarter of an hour. It changed to be a distance of 10. But then in that next 30 minutes, he's just staying 10 miles away from home, staying at the donut shop. Okay, but we need to figure out what t value ends this interval. So we knew that 7:15 corresponded with t equals 1/4. Here we see that we have 30 minutes elapsing, or half an hour. So we want to take that time value, the interval that the value that starts this interval of time, this 1/4, and we want to add a half hour to it. Okay, we want to add the 30 minutes, the 1/2 hour that will correspond to 7:45. So what I'm asking for here is, what is 1/4 plus 1/2? Okay, so 1/4 plus 1/2, hopefully we're okay with seeing that that would be 3/4. So what this is telling us is that for a quarter hour past 7 a.m. up until 3/4 of an hour past 7 a.m., Martin is staying at the or the donut shop. Okay, so I'm going to erase. I actually just might move this graph, because maybe I'll add to it as we keep going. But so far we have then just that constant function of 10, that constant distance being 10 miles away from home. So this idea of staying 10 miles from home, and he's doing that for this interval of time. So then we see in our scenario, it says that now he's got to make up for lost time, right? So from 7:45 up until, I think, 8:05, right? That would be the next chunk of time, the 20 minutes. Okay, so for 20 minutes, he's traveling at a different rate. For 20 minutes, it says in 20 minutes, he goes 18 miles. Okay, so we have 18 miles are covered in 20 minutes. We can convert that to miles per hour. So we can strategically multiply by 60 minutes over 1 hour in order to get the units of minutes to cancel out. And that leaves us with the rate of, I believe it was 54 miles per hour. I'm going to move this graph one more time. We will use that later. But for right now, we see that 20 will divide into 63 times 3 times 18 times 18 gives us that 54 miles per hour. Okay, so that's our slope, right? Our slope is 54 miles per hour. The point that started this segment, right, I'm going to just choose to use the starting point of this segment just to kind of keep it consistent. The point that started this segment was the point 3/4, 10, which said that at 7:45, 3/4 of an hour after 7, Martin was 10 miles away from home. So I can again put that into point slope form and see the slope of 54, t minus my time value, and then plus my distance value of that point. So that would be my third function, that function that describes when Martin is driving at a rate of 18 miles in 20 minutes. But we do have this kind of annoying piece over here, right? We need to figure out what t-values is this occurring for. So we saw previously that this change in his commute, right, this speeding up in his commute started at t is 3/4, and it's ending 20 minutes later. So 20 minutes later would be a third of an hour later. So we want to think 3/4 of an hour plus a third of an hour later. Getting our common denominators would be 9/12 plus 4/12, which would give us 13/12. So 13/12 of an hour after 7 a.m., this part of Martin's commute ends. Okay, so what this is saying is that 3/4 of an hour, oops, let me bring that back. So what this interval of time is discussing is that 3/4 of an hour after 7 a.m. up until 13/12 of an hour after 7 a.m., aka from 7:45 to 8:45, Martin is traveling in a way that is modeled by this linear piece, right? He's leaving the point 3/4, 10 at a slope of 54, right? At a rate of 54 miles per hour. So I'm going to just go ahead and erase this this addition of the fractions here to give us some space to finish this off. We have to finish getting Martin to school, right? Unfortunately, at 8:05, right, this 8:05, which is corresponding to that 13/12 of an hour after 7 a.m., Martin's car breaks down, okay, and he's forced to jog to school. So his jog takes 45 minutes, so 8:05 to 8:50, Martin is jogging at a rate of 3 miles in 45 minutes. We can convert that to our distance unit that we define to be miles and compare that against our time unit that we define to be hours since 7 a.m. So we want to go miles per hour. So we have 60 minutes per 1 hour, as we've seen before, seeing that those minutes cancel out. I know that 3 actually divides into 45 15 times, and then 15 divides into 60 4 times. So this gives us a rate of 4 miles per hour. So this tells us that our slope is 4 miles per hour, and the point at which he started this portion of his commute, right, when his car broke down, that was at the end of the last piece, right? That was at t is 13/12. And we got to think about, well, how far away was he from home, right? In the first piece of his commute, up here, before he got to the donut shop, he traveled 10 miles, okay? So maybe it would be helpful to remind ourselves, here he made it 10 miles from home. Here he stayed 10 miles, right? In this third portion of his commute, he traveled 18 more miles. So when he's starting the jog portion of his commute, he is actually 28 miles from home. Okay? So we can go ahead and put this into point slope form, a slope of 4, a point 13/12 plus 28. So that would be our last function that's going to build our piecewise function. Okay, and then lastly, we have to figure out, well, what t-values is this function defined for? For what values of t is Martin jogging? So 8:05 corresponded with the t-value of 13/12. So let me kind of stay consistent with how I've been doing this. 8:05 again, that was your 13/12. And then 45 minutes later, okay, so 45 minutes later, or 3/4 of an hour later, Martin has made it to school. So we want to figure out what is 3/4 plus 13/12. Okay, so we want to take 13/12, that time that his jog started at, and we want to add the 45 minutes that he jogged for. So doing that addition, getting that common denominator, gets us 13/12 plus 9/12, which equals 22/12, which equals that 11/6 that we saw in class. So 11/6 of an hour, almost 2 hours after 7 a.m., Martin is arriving to school. Okay, so these are all the pieces that make up our piecewise function. Written in this way, it is not our piecewise function. So I'm going to go ahead and scroll down because I've run out of room. Down here on this last page, I'll show you how to put this all together. So our d of t, our output value, our distance from home, is defined by 4 different pieces. It was defined by that linear piece where Martin was traveling at a rate of 40 miles per hour. He did that for 15 minutes. It was then defined by that constant piece of 10 where he just hung out at the donut shop. He stayed at the donut shop for 30 minutes. And then not lastly, there's still 2 more pieces. Then he drove pretty quickly. Right here, he sped up to that 54 miles per hour from leaving the donut shop at time equals 3/4 and being 10 miles away from home. For that, that part of his commute took 20 minutes, and we can show that 20 minutes in 3/4 is less than t, which is less than 13/12. And then lastly, he unfortunately had to jog, right? He's traveling at 4 miles per hour there, and jogging from time is equal to, from the point time is 13/12, and distance from home is 28. And that is occurring for 45 minutes. That would be 13/12 less than t less than or equal to 11/6. So this would be our final answer for question 1. Okay, all of this stuff up here is how we got there. And as you can see, it's pretty involved. Okay, we have to take apart piece by piece what's happening in his commute to start, how long is it happening for, what's happening in his commute next, and how long. Okay, so we have a lot of unit conversions to keep track of, but my hope is that this video cleared up what we did in class.